There is a structure buried inside an ancient story that most people have read entirely wrong. Not wrong in the way that myths are usually misread, where we've lost the metaphor, or confused the symbolism, or collapsed some nuanced religious teaching into a children's book illustration. Wrong in a more unsettling way than that. Wrong because when you strip away the theology and the allegory and the Sunday school version, when you take the Tower of Babel story at its barest literal face value and ask a very simple, very modern question, could a tower like that actually have been built? And if so, what would have stopped it? The answer you get back from physics is not what you expect. It is not comfortable. And it does not let you go. Here is what most people think the Tower of Babel story is about. A group of ancient people, united by one language, decide to build a tower tall enough to reach heaven. God sees this, finds it presumptuous, and confuses their language so they can no longer cooperate. Construction halts. Humanity scatters. The tower is never finished. The lesson, presumably, is something about hubris. Don't overreach. Know your place. The end. Except that is not actually what the text says. And the moment you read it carefully, really carefully, a different and considerably stranger story emerges. The book of Genesis, chapter 11, says this: "The people came together and said, 'Come, let us build ourselves a city and a tower with its top in the heavens, and let us make a name for ourselves, lest we be dispersed over the face of the whole earth.'" The divine response is remarkable. It does not say this is impossible. It does not mock their ambition. It says, and this is the part that tends to get skipped over in popular tellings, nothing that they propose to do will now be impossible for them. Read that again. Nothing that they propose to do will now be impossible for them. Whatever your relationship with ancient religious texts, that sentence is extraordinary. The reason given for intervening is not that the tower is laughably unrealistic. The reason given is that if left unchecked, these unified, cooperative, inventive humans will actually succeed at whatever they attempt. The tower to heaven is presented not as delusion, but as a genuine trajectory. The concern is not that they are foolish. The concern is that they are capable. So what happens when you take that seriously? What happens when you stop reading Babel as a parable about the folly of ambition and start reading it as an engineering problem? What happens when you ask, with everything we now know about materials science, atmospheric physics, gravitational mechanics, and structural engineering, exactly where and how a tower ascending into the sky would fail? The answer is that it would fail, spectacularly and inevitably, but not for the reasons you would guess, not because ancient people lack the knowledge or the will or the labor. The failure modes that would kill a tower reaching for the heavens are deeply, almost poetically woven into the fabric of physical reality itself. They are not engineering problems that better technology can fix. Some of them are consequences of laws that apply universally, to everyone, at every level of technological development. They are failures baked into the universe. And here is the part that should genuinely unsettle you. Several of those failure modes were not understood by anyone on Earth until well after Newton. Some were not fully understood until the 20th century. The people who wrote the Babel story could not possibly have known about atmospheric pressure gradients, or the Kármán line, or the compressive limits of stone under its own accumulated weight. They could not have run the structural calculations. They did not have the physics. And yet the story lands structurally precisely on the right problem. It stops exactly where the physics says it should stop. Whether you call that coincidence, or cultural memory, or something else entirely, that is a question you get to decide for yourself. But the overlap is real, and it is worth examining very, very carefully. Because somewhere between the ancient mud plains of Mesopotamia and the cold equations of modern physics, there is a tower that never got built, and the story of why is stranger than the myth. There is a place in southern Iraq, roughly 200 kilometers southeast of Baghdad, where the land is so flat and so ancient and so utterly indifferent to human ambition that standing in it feels like standing at the beginning of time. The Euphrates has carved its slow path through this landscape for longer than recorded history can reach. The air is hot and dry and heavy with dust. And somewhere beneath the cracked surface of that plain, under centuries of accumulated silt and rubble and the compressed remains of civilizations that rose and collapsed and were forgotten entirely, there are bricks, millions of them, hand-pressed, sun-dried, stamped in many cases with the name of a king. The place is called Babylon, and the king whose name appears on those bricks, on an almost obsessive number of those bricks, as though the act of stamping his name into clay was itself a form of immortality, is Nebuchadnezzar II. And if there is a single human being at the center of the Tower of Babel story, the one figure whose life and ambitions and almost incomprehensible construction projects form the historical skeleton beneath the myth, it is him. To understand Nebuchadnezzar is to understand something important about why the Babel story exists at all. He was not a minor regional ruler. He was, by any honest measure, one of the most powerful men who had ever lived up to that point in human history. He ruled the Neo-Babylonian Empire from 605 to 562 BCE, a reign of more than 4 decades, during which he transformed Babylon from a great city into something that contemporary observers described in terms that bordered on the supernatural. The Greek historian Herodotus, writing in the 5th century BCE, described Babylon as a city surpassing in splendor any city in the known world. That was not hyperbole for literary effect. It was the considered assessment of a man who had traveled extensively and seen the great cities of Egypt, Greece, and Persia. The city that Nebuchadnezzar built had walls thick enough to race chariots along the top. It had the Ishtar Gate, faced in brilliant blue glazed tile and decorated with golden dragons and bulls, a structure so overwhelming in its beauty and scale that fragments of it, reassembled in the Pergamon Museum in Berlin, still stop visitors cold today. It had the Hanging Gardens, which may or may not have existed, but which were celebrated across the ancient world as one of its 7 wonders. And it had at its center a structure called Etemenanki. That name in Sumerian means something that matters enormously for this conversation. It means house of the foundation of heaven and earth. And Etemenanki was a ziggurat, a massive, stepped, pyramidal temple tower that by the most serious scholarly reconstructions stood at least 90 meters tall, possibly more. Some estimates push it higher. 90 meters is not nothing. 90 meters is roughly the height of a modern 30-story office building. It was the tallest structure in Babylon. It may, at certain points in history, have been among the tallest structures on Earth. Most scholars today believe that Etemenanki is the historical seed from which the Tower of Babel story grew. The connection is not speculative. The Hebrew word Babel is simply the Hebrew rendering of Babylon. The linguistic relationship is direct. And the Jewish community that would have been most exposed to Etemenanki was the Jewish population that Nebuchadnezzar himself deported to Babylon following his conquest of Jerusalem in 597 BCE, and again after 587 BCE, the period known as the Babylonian captivity. Think about what that means for a moment. A people who have just watched their city destroyed, their temple burned, and their community forcibly relocated, now find themselves living in the shadow of the most audacious building project on Earth. Etemenanki would have been visible from vast distances across the flat Mesopotamian plain. It was designed to be. It was a declaration in mud brick and ambition that Babylon was the center of the universe and that its king was the instrument of the gods. For the Jewish exiles processing that trauma, trying to make theological sense of catastrophic loss, are looking up at that tower every day. The Babel story as we have it is not a difficult imaginative leap. It is almost an inevitable one. But here is where the history gets genuinely fascinating rather than simply sad. Because archaeological investigation of the actual site of Etemenanke has been going on in fits and starts for well over a century. And what the excavations have revealed is simultaneously impressive and haunting. The German archaeologist Robert Koldewey excavated Babylon extensively between 1899 and 1917, working under extraordinary conditions, often with limited funding and in the face of bureaucratic obstruction from Ottoman authorities. What he found at the site traditionally identified as Etemenanke was a massive square foundation, roughly 90 meters on each side, built from millions of kiln-fired bricks. The superstructure was long gone, dismantled over centuries. The bricks quarried for other building projects the way ancient ruins always end up being cannibalized by whoever comes next. But the footprint remained vast, unmistakable, real. Later, a clay tablet was discovered, now known as the Esagila tablet, housed in the Louvre, that appears to contain ancient technical specifications for the ziggurat itself. Dimensions, stage heights, the number of construction phases. It is not a complete blueprint in any modern sense, but it is close enough to one that when architectural historians and engineers have used it to attempt reconstructions, the results are consistent and credible. The tower appears to have risen in 7 stages, each one set back from the one below, tapering upward toward a temple at the summit dedicated to Marduk, the chief god of Babylon. And then there is a Greek source that ties everything together in a way that still sends a slight chill through you when you read it. In the 4th century BCE, Alexander the Great arrived in Babylon. Etemenanke, by that point, was in a state of serious disrepair, partially collapsed, its upper stages crumbling. Alexander, being Alexander, immediately ordered it restored to its original glory. He set 10,000 workers to the task of clearing the rubble from the base before reconstruction could begin. 10,000 workers. Clearing rubble alone. The scale implied by that number tells you something about how much material had accumulated, and therefore how tall the original structure must have been. Alexander died before the restoration was completed, and the project was abandoned. The rubble was never fully cleared. The tower was never rebuilt. There is something quietly devastating about that. The greatest conqueror the ancient world had ever seen, in possession of essentially unlimited resources and military labor, he looked at the ruins of Etemenanke and decided he wanted to restore it, and even he couldn't quite manage it. Which brings us to the question that the ancient sources never thought to ask, because they didn't have the tools to ask it properly. Not the theological question of whether humanity should have tried, the engineering question, the physics question, the question of what would actually have happened if Nebuchadnezzar or anyone else in the ancient world had possessed the ambition, in the labor force and the material resources to build not a 90-meter ziggurat, but a tower that genuinely aimed at the sky, a tower that kept going, a tower with no predetermined stopping point. What would the universe do to it? Let us start with what the ancient builders actually had to work with, because before the physics can kill the tower, you need to understand what the tower was made of. Mesopotamia is not a place that gives you granite. It is not a place that gives you marble, or sandstone, or any of the dense load-bearing rock that Egyptian builders had access to when they were raising pyramids. The Nile Valley sits near quarries. The Tigris-Euphrates plain sits near nothing except river clay and reeds, and the occasional patch of bitumen seeping up through the ground. What Mesopotamian builders had, in effectively unlimited quantities, was mud. And what they did with that mud, pressing it into rectangular blocks, drying it in the sun, or firing it in kilns, stacking it with bitumen mortar was genuinely ingenious given the constraints. But it was still, fundamentally, mud brick. And mud brick has physical properties that matter enormously once you start thinking about what happens when you stack it very, very high. The compressive strength of ancient sun-dried mud brick sits somewhere around 1 to 2 megapascals. Kiln-fired brick is better, perhaps 4 to 5 megapascals under ideal conditions. For comparison, modern structural concrete operates at 20 to 40 megapascals. Good quality granite sits above 100, so you are beginning already with a material that is somewhere between 20 and 100 times weaker than what modern engineers would reach for when building tall structures. That gap is not an abstract engineering footnote. It is a physical ceiling on how high you can go before the material at the base of your structure simply cannot hold the weight of everything above it. There is a number that structural engineers use called the theoretical maximum height of a structure, the point at which a column of any given material will crush itself under its own accumulated weight before it can be built any higher. For steel, that number is enormous, well beyond anything we have actually built or are likely to build in the near future. For reinforced concrete, it is still extraordinarily large. For mud brick, in even the best kiln-fired variety the ancient world could produce, the theoretical self-crushing height is somewhere in the range of 2 to 3 kilometers, assuming a solid column with no taper, no hollow sections, and perfect material consistency throughout. 2 to 3 kilometers sounds like a lot until you understand what we are actually comparing it against. The edge of space, the boundary where Earth's atmosphere becomes thin enough that the concept of flight as we understand it ceases to be meaningful, is defined by international convention at 100 kilometers above sea level. This is the Kármán line, named after the Hungarian-American physicist Theodor von Kármán, who calculated it in the mid-20th century. 100 kilometers. That is the minimum distance you would need to travel, straight up, before you could reasonably claim to have left Earth's atmosphere and entered what we would recognize as the beginning of space. 100 kilometers. Let that sit for a moment, because it deserves to. The driving distance from London to Birmingham is roughly 160 kilometers. You can cover that in under 2 hours on a motorway, feeling mildly bored and wondering whether you should have taken the train. The distance that separates the surface of the Earth from the edge of space is shorter than that drive. Shorter than the distance between Paris and Brussels. Shorter than the length of the English Channel at its widest point. In terms of horizontal distance, 100 kilometers is nothing. A long afternoon cycling, a short flight, a distance that modern infrastructure crosses without ceremony. Vertically, pointed straight up into the sky, it is everything. It is the entire thickness of the shell that makes Earth habitable. It is the difference between here and the void. And against that distance, our hypothetical Babel Tower, made of the best mud brick ancient Mesopotamia, could produce, would, at theoretical maximum, reach perhaps 2 to 3 kilometers before crushing itself. That is 2 to 3% of the way to the Kármán line. On a scale model where the Kármán line is represented by a ceiling 10 meters above your head, the mud brick tower reaches, at absolute best, somewhere around 20 to 30 centimeters off the floor. About the height of this page held upright, but let us be extraordinarily generous. Let us abandon mud brick entirely and assume, for the sake of exploration, that our ancient builders had access to something much better. Let us give them limestone. The Great Pyramids of Giza are built from limestone, and they have stood for roughly 4,500 years, which is as good an advertisement for the material's longevity as you are ever going to find. Limestone has a compressive strength of somewhere between 50 and 200 megapascals, depending on its grade and the presence of fractures. The theoretical self-crushing height for a solid column of good limestone is, very roughly, in the range of 20 to 30 kilometers. 20 to 30 kilometers is considerably more impressive. It is above the cruising altitude of commercial aircraft, which typically fly between 9 and 12 kilometers. It is up into the stratosphere, the layer of atmosphere that sits above the turbulent weather systems of the lower troposphere and is home to the ozone layer. Standing at the top of a 30-kilometer limestone tower, assuming you could breathe, which you absolutely could not, and we will come to that, you would be looking down on the clouds. You would be above the kind of weather that grounds flights and collapses roofs. You would, in any intuitive sense, be genuinely high up in a way that would have felt, to ancient eyes, like approaching the realm of the divine. And you would still be 70 kilometers from space. You would have covered less than a third of the distance to the Kármán line. You would not even be close. For a sense of what that gap feels like, consider Mount Everest. At 8,849 meters above sea level, Everest is the highest point on the surface of the Earth. Climbers who reach its summit experience oxygen levels roughly a third of what exists at sea level. The conditions are lethal without supplemental oxygen, and even with it, the human body begins to deteriorate measurably within hours. Everest is as high as the natural world, unaided by engineering, has ever put a human being, and Everest is less than 9% of the distance to the Kármán line, less than 1/10 of the way. The atmosphere that protects us and sustains us is almost incomprehensibly thin relative to the size of the planet it wraps around. If you shrunk Earth to the size of a standard classroom globe, the entire atmosphere, all of it, the air you are breathing right now, the weather systems, the ozone layer, everything, would be a film less than a millimeter thick. You would barely be able to feel it with your fingertip. That is the shell our hypothetical tower would need to punch through, and the geometry of punching through it with materials drawn from the surface of the Earth is, as we are beginning to see, somewhere between profoundly difficult and outright impossible. But the structural limits of the material are only the first problem. And in some ways they are not even the most interesting one, because once you start asking what happens to a human being as the tower rises, the physics gets considerably more personal. Start with the air, because the air is where the first truly non-negotiable physical barrier appears, and it appears much sooner than most people would instinctively expect. At sea level, the atmosphere exerts a pressure of approximately 101,325 pascals on every surface it touches. You do not feel this because your body has evolved to operate within it, and the pressure inside you balances the pressure outside. But that pressure, that constant, invisible weight of the atmosphere pressing down from above, is the product of every molecule of air stacked up between you and the vacuum of space. It is the cumulative weight of the entire atmospheric column sitting on top of you. And as you rise, that column gets shorter. The air above you gets thinner. The pressure drops. This is not a gradual, gentle process that gives your body time to adjust gracefully. It is relentless, and it follows an exponential curve. By the time you reach 5.5 kilometers of altitude, roughly the height of base camp on the southern approach to Everest, the atmospheric pressure has already dropped to half of what it is at sea level. Half. You have not even left the lower atmosphere yet, and you are already breathing air that is half as dense as what you started with. Your body, without acclimatization, begins to struggle almost immediately at these altitudes. Cognitive function degrades. Your physical coordination deteriorates. The condition has a clinical name, acute mountain sickness, and in its severe forms it kills. At 8 kilometers, you enter what mountaineers call the death zone. The name is not melodramatic. At these altitudes, the human body cannot acclimatize. It can only deteriorate. Even the most elite, most acclimatized, most physically extraordinary climbers on Earth can survive in the death zone for only a limited number of hours before the lack of oxygen begins causing irreversible neurological damage. The cells of the brain and heart require oxygen continuously, and above 8 kilometers. No matter how hard you breathe, you cannot pull enough of it from the thinning air to sustain full physiological function. You are dying, just slowly enough that it is not immediately obvious. Now translate that into the tower. Your Babel builders, working in the open air, hauling materials upward, performing the physically intense labor of construction, they would begin experiencing altitude sickness symptoms well below 5 kilometers. Serious cognitive impairment and coordination loss would follow before they reached 8. The death zone would be encountered at heights our generous limestone tower could theoretically still achieve structurally. So long before the material crushes itself, the workers building it would be incapacitated. You cannot build a tower when the people building it cannot think clearly, cannot coordinate, cannot breathe adequately, and are quietly dying from hypoxia. The ancient text says God confused their languages. Physics suggests the atmosphere was prepared to do something considerably more direct, but there is a pressure problem that operates entirely separately from the oxygen content of the air, and this one is almost more philosophically uncomfortable because it has nothing to do with biology at all. It is a problem for the structure itself. Wind, specifically wind at altitude. At ground level, wind is something you experience as weather. It is inconvenient, occasionally dramatic, sometimes dangerous. But the winds that exist in the lower troposphere, the layer of atmosphere extending from the surface to roughly 12 kilometers, are relatively tame compared to what waits above. The jet stream, that river of fast-moving air that circles the planet in the upper troposphere and lower stratosphere, moves at speeds regularly exceeding 250 kilometers per hour, and in extreme cases reaching beyond 400. These are not gusts. These are sustained, consistent winds that circle the entire planet at altitude, and they apply continuous lateral force to anything that exists within them. A tall structure is essentially a lever, and the taller the lever, the greater the rotational force applied at its base by any lateral load. This is why engineers have a concept called the overturning moment, the tendency of a tall structure to rotate about its base and topple when wind pushes against its upper sections. The overturning moment scales with both the wind force and, critically, the height at which that force is applied. Wind pushing against the top of a 500-meter structure applies a rotational force at the base that is 500 times greater than the same wind pushing against a point 1 meter off the ground. Extend the height to 5 kilometers, and the numbers become, very quickly, almost impossible to engineer around with ancient materials. The Burj Khalifa in Dubai, currently the tallest building on Earth at 828 meters, it has a highly sophisticated tapered design specifically engineered to reduce wind loads at its upper sections. It has a Y-shaped floor plan that breaks up the coherent shedding of wind vortices. It has tuned mass dampers, enormous counterweights inside the structure that oscillate to cancel out wind-induced vibrations. It has teams of engineers who spent years modeling wind behavior in computational fluid dynamics software before a single foundation stone was laid. And even with all of that, the Burj Khalifa sways perceptibly at its upper floors in high winds. The sway is designed in. It is not a flaw, it is how the building survives. Ancient mud brick has no dampers. It has no tapering algorithm. It has no computational fluid dynamics. It has no steel reinforcement distributing lateral loads through a redundant structural network. Mud brick is a compressive material. It handles weight pushing straight down with reasonable competence. What it handles very badly is bending. Apply a lateral load to a tall mud brick structure and you are asking the material to perform in tension, to resist being pulled apart on one side as it is being compressed on the other. Mud brick is genuinely terrible at this. Its tensile strength is a fraction of its already modest compressive strength. The lateral forces that sustained altitude winds would impose on a tower of any serious height would not bend the structure gradually and visibly. They would crack it, i.e. suddenly and catastrophically, at the point of maximum bending stress. And we have not even discussed resonance yet. Every structure has a natural frequency, a rate at which it will preferentially oscillate if excited. Wind does not blow at a perfectly steady rate. It is turbulent, variable, and it generates oscillating pressure differences as it flows around obstacles. If the frequency of wind-induced pressure variations matches the natural frequency of the tower, the oscillations build. Each cycle adds a little energy to the system. The structure begins to sway with increasing amplitude. This is resonance, and it is what destroyed the Tacoma Narrows Bridge in 1940, a modern steel suspension bridge, carefully engineered, brought down not by a hurricane, but by a moderate wind blowing at exactly the wrong frequency. The bridge oscillated, the oscillations amplified, and the structure tore itself apart in a matter of hours while people watched and filmed it and could not quite believe what they were seeing. A mud brick tower of serious altitude in sustained wind is a resonance disaster waiting to occur. With no damping mechanism, no active response system, no flexibility designed into the structure, the oscillations build until the material fails. The failure would not look like a tower being pushed over. It would look like a tower shaking itself to pieces. There is another factor that the ancient world could not have conceived of, and it concerns the Earth itself. The Mesopotamian plain is not geologically stable in the way that, say, exposed bedrock in a shield region is stable. It is river delta sediment, deep, unconsolidated alluvial deposits laid down over millions of years by the Tigris and Euphrates. This material has a property called liquefaction potential. Under sufficient dynamic loading, which is to say, under seismic activity or sustained vibration, it can temporarily lose its structural cohesion and behave more like a liquid than a solid. The foundation-bearing capacity of river delta sediment is a fraction of what you would get from bedrock. Modern engineers building on such ground drive piles deep, sometimes many tens of meters, to reach material with adequate load-bearing capacity. They calculate settlement, the gradual sinking of heavy structures into soft ground, and design their buildings to tolerate it evenly. They monitor continuously. The ancient builders of Mesopotamia knew, in a practical sense, that foundation quality mattered. The ziggurat at Ur, one of the best preserved ancient Mesopotamian temple towers, shows evidence of deliberate ground improvement beneath its foundation. Layers of reed matting and bitumen used to distribute loads and reduce differential settlement. That is genuinely sophisticated engineering intuition for 3,000 years ago. But there is a limit to what reed matting can do. As height increases, the loads transmitted to the foundation increase proportionally. And at some point, the soft delta sediment beneath the great Mesopotamian plain would simply give way. The tower would not collapse dramatically from the top. It would begin to sink unevenly into the ground from the bottom. It would tilt. Tilt introduces lateral stress. Lateral stress in mud brick, as we have established, ends badly. Now move above 10 kilometers into the stratosphere, and the problems change character entirely. The temperature at the tropopause, the boundary between the troposphere and the stratosphere, drops to around minus 55 degrees Celsius. In the stratosphere itself, temperature actually rises with altitude due to ozone absorption of ultraviolet radiation, reaching around 0 degrees Celsius at the stratopause, 50 kilometers up. These temperature variations are not simply uncomfortable for hypothetical workers. They are structurally relevant. Materials expand and contract with temperature. Mud brick, stone, and bitumen mortar all have thermal expansion coefficients, and when sections of a very tall structure experience dramatically different temperatures, the base in Mesopotamian heat, the upper sections in stratospheric cold, the differential expansion and contraction introduces stress cycles that are the engineering equivalent of repeatedly bending a paperclip back and forth. Eventually, it breaks. Above the stratosphere, in the mesosphere extending from 50 to 85 kilometers, temperatures plunge again to as low as -90 degrees Celsius near the mesopause. This is the coldest region of Earth's atmosphere. It is also the region where meteors typically burn up, the friction of atmospheric entry at high speed, generating enough heat to vaporize rock and metal. A tower extending into the mesosphere would encounter micrometeorite impacts regularly. Not the dramatic Hollywood fireball variety, something quieter and more persistent. A slow erosion of the upper sections by particles moving at cosmic velocities. Ancient mortar does not heal itself. And then at around 100 kilometers, you reach the Kármán line, and the atmosphere becomes so thin that conventional aerodynamics ceases to function. The air pressure is less than 1/1,000,000th of what it is at sea level. The temperature fluctuates wildly depending on whether you are in sunlight or shadow, swinging between extremes that would shatter most materials. Any gas trapped within the tower's construction, in cavities, in porous brick, in mortar joints, would expand explosively as external pressure dropped towards zero, as though the structure itself were trying to turn inside out. At this altitude, you also encounter the ionosphere, the region of the atmosphere ionized by solar radiation, and with it, the charged particle environment of near-Earth space. Cosmic radiation, which is deflected by the magnetic field and absorbed by the atmosphere at lower altitudes, arrives here at meaningful intensity. The cumulative radiation dose at the Kármán line would be biologically lethal for extended exposure. And the electrical environment, the ionosphere, is the upper plate of a vast natural capacitor, with the Earth's surface as the lower plate, and constantly discharging in the form of lightning, would make a vast conductive structure reaching from the surface to the ionosphere something close to the world's largest lightning rod. A lightning rod so efficient it would attract not the random strikes of ordinary thunderstorms, but sustained electrical discharge from above. The tower would not be struck by lightning occasionally. It would be conducting electricity continuously. None of this was knowable to anyone in ancient Mesopotamia, in ancient Rome, or in medieval Europe. Some of it wasn't knowable to anyone anywhere until the 20th century. The atmosphere's structure, the existence and nature of the troposphere, stratosphere, mesosphere, thermosphere, and ionosphere was not mapped until aircraft and balloons and eventually rockets made it possible to actually probe those regions directly. The jet stream was not discovered until World War II. Pilots noticed unexpected headwinds at high altitude. The Kármán line was not calculated until 1957. The full picture of what exists between the ground and space, all the layers of it, all the hostility encoded in those layers, is genuinely modern knowledge. And yet the ancient intuition encoded in the Babel story that something above intervenes to stop the tower, that the effort of building fails not because of lack of will or lack of labor, but because of something inherent in the nature of what is being attempted. That intuition, it turns out, was not wrong. It was just working from a much smaller data set than the universe actually contains. Here is the uncomfortable admission that serious scholarship has to make about the Tower of Babel, and it is one that tends to get glossed over in both religious and secular discussions of the subject. We do not actually know, with any certainty, what the original story was describing, where it came from, how old it is, or whether the physical structure we have identified as its historical basis is genuinely the right one. The confidence with which popular culture handles the Babel narrative, treating it as either obvious religious allegory or obvious historical record, depending on which side of that fence you are standing on, is not really warranted by what the evidence actually supports. The gaps in our knowledge are significant, and they are interesting. Start with the text itself. The Tower of Babel account in Genesis is 11 verses long. 11 verses. It is one of the shortest narratives in the entire Hebrew Bible, and it is embedded in a section of Genesis dealing with primordial prehistory, the period before Abraham, before the patriarchs, before anything that historians can attach to datable events. The narrative gives no names other than Babel. It gives no king, no architect, no date, no precise location beyond the plain of Shinar, which is a general geographical term for the Mesopotamian lowlands, covering an enormous area. It gives no description of the tower's dimensions, its design, or how far construction progressed before it stopped. For a story that has generated thousands of years of commentary, theological debate, and cultural resonance, the source material is remarkably sparse. Scholars of the Hebrew Bible have debated for centuries exactly when this story was written, by whom, and what its relationship is to the surrounding material. The documentary hypothesis, the dominant framework in academic biblical scholarship since the 19th century, suggests that the Pentateuch, the first 5 books of the Hebrew Bible, was compiled from multiple earlier source documents, traditionally labelled J, E, D, and P, representing different authorial traditions with different theological emphases and different historical contexts. The Babel story is generally attributed to the J source, the Yahwist tradition, but even within that attribution there is debate about dating. Some scholars place the composition in the 10th or 9th century BCE, during the early Israelite monarchy. Others argue for a later date, during or after the Babylonian exile, which would place the story's finalized form squarely in the context of direct Israelite experience of Babylon and Etemenanke. The honest answer is that we cannot determine this with precision from the evidence currently available. The relationship between the biblical Babel story and earlier Mesopotamian traditions is equally difficult to pin down. There are Sumerian texts, significantly older than the Hebrew Bible, that discuss a primordial time when all humanity spoke a single language and divine intervention that ended that unity. The most cited is a Sumerian text sometimes called the Enmerkar epic, involving a Sumerian king's relationship with the city of Arata, in which the god Enki is said to have confused the tongues of humanity. The parallels with the Babel story are real enough that scholars have long debated a direct literary relationship. The possibility that the biblical narrative derives, directly or through several intermediate steps, from much older Mesopotamian source material. But proving that relationship definitively, establishing the exact chain of transmission, is not currently possible. The textual evidence is suggestive rather than conclusive. Then there is the archaeological question of what Etemenanke actually looked like, and here the limits of what we can recover from the ground are genuinely frustrating. Robert Koldewey's excavations at the end of the 19th and beginning of the 20th century revealed the foundation outline. The Esagila tablet provides some dimensional data, but the superstructure is gone. Not damaged, not partially standing, gone, systematically dismantled over centuries by people who needed the bricks for other purposes. Ancient bricks in Mesopotamia were valuable enough that finished structures were routinely deconstructed and their materials reused, and Etemenanke suffered this fate repeatedly after Babylon's political decline. What we have is the footprint and some textual description. The actual appearance of the tower, its precise height, the exact profile of its stages, the nature of the temple at its summit, involves a substantial degree of informed reconstruction that honest archaeologists describe as their best current interpretation rather than established fact. There is also a deeper problem with the identification of Etemenanke as the Babel Tower specifically. Mesopotamia had many ziggurats. The ziggurat at Ur, built around 2100 BCE during the 3rd dynasty of Ur, and he predates Nebuchadnezzar's Babylon by 15 centuries and is better preserved than anything at Babylon itself. There were ziggurats at Nippur, at Uruk, at Eridu, at Assur. The ziggurat form was a standard feature of Mesopotamian religious architecture across thousands of years and hundreds of kilometers. The case for Etemenanke being the specific historical seed of the Babel story rests primarily on the linguistic connection between Babel and Babylon and on the timing of the Babylonian exile. It is a strong case. It is not an airtight one. And then, sitting behind all of these historical and textual uncertainties, there is the broader scientific question of what would actually happen to a tower of truly extreme height. And here too, our knowledge has limits that are easy to underestimate. The failure modes we have discussed are real and well understood at engineering scales we have actually tested. But there are regions of the atmosphere we have never built anything into, and the behavior of structures in those environments involves extrapolation from physical principles rather than empirical data. We have never built a structure above a kilometer or so in height. The Burj Khalifa at 828 meters is our current outer limit for inhabited structures. What happens structurally to a continuous rigid tower at 10 kilometers, at 30, at 80, we can calculate theoretically, but the calculations rest on models of atmospheric and material behavior that have not been validated at those scales. This is not a trivial admission. Science is a process of building models and then testing them against reality, and where we cannot test directly, our models carry uncertainty proportional to how far outside validated experience they reach. The physics says very clearly that a tower reaching the Kármán line is impossible with any material available on Earth's surface. But the precise cascade of failure, exactly where, exactly how, exactly in what sequence the structure would begin to fail as height increased, involves more modeling uncertainty than popular science communication usually acknowledges. What we can say with confidence is this: the barriers are real. The physics is hostile. The atmosphere is not a passive empty space waiting to be filled with human construction. It is a dynamic, layered, a variable environment that would actively resist and ultimately destroy any fixed structure ambitious enough to challenge its full extent. The story that something intervenes to stop the tower is, in physical terms, entirely accurate. It just turns out that the something is thermodynamics, fluid dynamics, material science, and geophysics rather than divine displeasure. Whether that makes the story more or less remarkable is a question worth sitting with for a moment. Begin the journey at ground level, in the heat of the Mesopotamian plain, because that is where any honest attempt at this tower has to start. Not with ambition or theology or myth, but with the basic practical problem of foundation. The ground beneath ancient Babylon is, as we have established, river delta sediment. Deep, soft, compressible, alluvial clay deposited over millions of years by the meandering of two of the world's great rivers. Before a single brick is laid above ground level, the engineers of our hypothetical tower face a problem that would consume enormous resources and ingenuity just to solve adequately, let alone optimally. Modern engineers building on comparable ground in cities like Shanghai or Amsterdam or Houston drive steel piles tens of meters into the earth to reach load-bearing strata. They install monitoring systems that track millimetric settlement continuously over years. They design foundations with deliberate redundancy so that differential settlement, The uneven sinking of different parts of the foundation at different rates does not introduce the fatal lateral stresses that cause tall structures to tilt and fail. The ancient Mesopotamians had none of this. What they had was accumulated practical wisdom, the understanding that broader foundations distribute load more effectively, that reed matting and bitumen could help stabilize soft ground, that a structure's weight needed to be managed carefully through stepped design rather than attempting vertical walls from ground to summit. The ziggurat form was not aesthetically arbitrary, it was structurally rational. Each stepped reduction in cross-sectional area as the tower rose reduced the weight bearing down on the lower sections, and the broad base distributed the total load over the maximum possible ground area. But here is the thing about step design in the context of a tower that aims for serious altitude. The mathematics of tapering work against you as height ambitions grow. If you want a structure that remains stable at its base under its own weight and the wind loads it will encounter, and if you are building from materials with the compressive and tensile strength of ancient brick, the base must be vastly wider than the summit. The ziggurat at Ur has a base of roughly 64 by 45 meters and stands about 30 meters tall. Its base area is enormous relative to its height. Now extrapolate that ratio to a tower aimed at even 1 kilometer of altitude, and the base required becomes wider than the city of Babylon itself, wider than most modern cities. Aimed at 10 kilometers, the base would need to be continental in scale. The tower at some point stops being a tower and becomes a mountain. And mountains, or it turns out, are exactly what geology produces when you pile enough material on the Earth's surface in one location. And they stop growing naturally at heights well below the Kármán line for reasons that are themselves deeply embedded in the physics of planetary crusts. The highest mountains on Earth exist because of the dynamic balance between tectonic uplift, the collision of crustal plates pushing rock upward, and erosion, which tears material back down. The Everest sits at 8,849 meters, not because the geology decided that was a satisfying number, but because that is approximately where the balance point sits between the forces building it up and the forces wearing it down. There is a theoretical maximum mountain height for Earth, determined by the compressive strength of crustal rock under gravitational loading, and it sits somewhere around 10 kilometers. Beyond that, the rock at the base would flow under the pressure, behave plastically rather than rigidly, and the mountain would spread laterally rather than growing taller. The planet itself imposes a ceiling on vertical ambition. Our tower, if built wide enough to be stable, would eventually run into the same limit. It would become, in effect, a man-made mountain. And man-made mountains hit the same ceiling as natural ones. This is one of those moments where the physics of the problem circles back and bites its own tail in a way that feels almost designed. You cannot build a thin tower because thin towers fall over or crush themselves. You cannot build a wide tower because wide towers become mountains, and mountains have a physical height limit imposed by planetary geology. The geometry of the problem from either direction converges on the same answer. The surface of the Earth is not a place from which a rigid structure can reach space. But let us keep ascending anyway, because the journey through what would happen is more instructive than simply cataloguing why it cannot be done. Imagine the tower has somehow cleared 5 kilometers. You are in the upper troposphere, above the weather systems that produce most of Earth's precipitation, in a region of thin, cold, fast-moving air. The temperature is around -20 Celsius and dropping. The wind, which was manageable at ground level, has been increasing steadily in speed as altitude grew and the slower friction-affected air of the lower atmosphere gave way to the freer flow of the upper troposphere. At 5 kilometers, sustained wind speeds of 60 to 80 kilometers per hour are entirely normal, and gusts significantly exceed that. The workers, if they exist at this altitude at all, are in serious physiological difficulty. Oxygen partial pressure has dropped to roughly half its sea level value. Without supplemental oxygen, a technology whose principles were not understood until the 18th century and whose practical implementation for altitude use came in the 20th, cognitive performance at 5 kilometers is measurably impaired. Reaction times slow. Judgment degrades. The fine motor coordination required for precision construction work deteriorates. And these workers are doing this while exposed to cold, wind, and whatever psychological vertigo accompanies being 5 kilometers above the ground on a structure that, by the time you are 5 kilometers up, is already more than 5 times taller than any building ever constructed by human beings. Now the tower reaches 8 kilometers, and something changes in the character of the problem. This is the death zone, and no amount of acclimatization overcomes what happens to human physiology here. The partial pressure of oxygen is low enough that even at rest, the body cannot adequately oxygenate its tissues. Active physical labor at this altitude, and construction is extremely active physical labor, accelerates oxygen depletion dramatically. A worker attempting to lay bricks at 8 kilometers altitude in the open air without supplemental oxygen would likely lose consciousness within minutes and die within hours. The mountain climbing record for sustained time in the death zone without oxygen is measured in hours, achieved by a handful of the most physiologically exceptional humans who have ever lived, under conditions of extreme mental preparation, careful acclimatization, and minimal physical exertion. So the human factor terminates somewhere between 5 and 8 kilometers. This is a hard ceiling for ancient construction by human labor, and it sits less than 10% of the way to the Kármán line. Whatever happens above 8 kilometers happens without workers. The tower, if it continues to grow, does so through some mechanism that does not require human beings at the construction site. No such mechanism existed in the ancient world. This is, in historical terms, where the project definitively ends, not because of will or resources or knowledge, but because the bodies doing the building simply stop working. But the physics does not stop just because the workers have. Above 10 kilometers, the tower enters the stratosphere, and here the environment changes character in ways that are easy to underestimate. The stratosphere is not simply cold upper atmosphere. It is a chemically active region dominated by the ozone layer, the band of ozone molecules between approximately 15 and 35 kilometers that absorbs the majority of the sun's ultraviolet radiation. The photochemical reactions happening continuously in the stratosphere release significant energy, and the radiation environment is considerably more aggressive than anything experienced at lower altitudes. Ultraviolet exposure at stratospheric altitudes without the protective filtering of the ozone layer below you is intense enough to cause severe biological damage within minutes. Any organic component of the tower's construction, wooden scaffolding, rope, organic mortar additives, would experience accelerated degradation at these altitudes simply from UV exposure. The temperature gradient in the stratosphere is unusual and structurally relevant. Unlike the troposphere, where temperature drops consistently with altitude, the stratosphere warms with altitude, from around -55 Celsius at its base to roughly 0 at the stratopause, 50 kilometers up. This temperature inversion creates the stratosphere's characteristic stability. There is very little convective mixing in the stratosphere, which is why aircraft and weather balloons can float within it relatively smoothly. But for the tower, this temperature inversion means that different sections of the structure experience dramatically different temperatures across a relatively short vertical span. A tower section at 15 kilometers altitude experiences perhaps -45 Celsius. A section at 40 kilometers experiences perhaps -5. The differential thermal expansion across this span, the way different sections of the structure try to expand or contract by different amounts in response to their local temperature, introduces cyclic stress that accumulates over time, working at mortar joints and material interfaces the way frost works at cracks in a road. Slowly, persistently, without rest. Above 50 kilometers, in the mesosphere, the temperature plunges again to the lowest values found anywhere in Earth's atmosphere, around -90 Celsius near the mesopause at 85 kilometers. The air here is so thin that sound propagates with great difficulty. Conventional aerodynamics has effectively ceased to function, and this is the region where meteors ablate, where rocks and metal fragments falling from space encounter enough atmospheric resistance to burn. The flux of micrometeorites at mesospheric altitudes is not dramatic by any visual standard, but over time, the cumulative impact of particles moving at cosmic velocities against the upper sections of the tower would erode material at a rate that has no counterpart in surface-level engineering experience. And then there is the electrical dimension of this altitude range that almost never appears in popular discussions of the subject. The global atmospheric electrical circuit, the continuous flow of electrical current between the ionosphere and the Earth's surface, maintained by thunderstorms acting as generators, produces a potential difference of roughly 300,000 volts between the ionosphere and the ground. Under normal conditions, this potential is distributed across the full thickness of the atmosphere, and the electric field at any given altitude is relatively modest. But a conductive tower extending through a significant fraction of this distance would short-circuit the local atmospheric electrical environment. It would create a preferential conduction path, drawing current continuously. The electrical effects at the summit of such a structure, in the vicinity of the ionosphere's active charge layer, would be extraordinary and almost certainly destructive. This is not occasional lightning. This is continuous electrical discharge on a scale that has no analogue in any engineering experience accumulated by human civilization. At 100 kilometers, the Kármán line, the atmosphere is so thin that molecules travel hundreds of kilometers between collisions. Pressure is effectively zero for engineering purposes. Temperature swings between extremes depending on solar exposure. In direct sunlight, surfaces reach temperatures exceeding 100 Celsius. In shadow, they drop to -100 and below within a single orbital period. There is no medium to conduct heat away from sun-exposed surfaces and no insulating air to slow cooling in shadow. Thermal management at these altitudes requires active engineering systems, heat pipes, reflective coatings, radiators, none of which existed in the ancient world. The atomic oxygen environment in the upper atmosphere also attacks materials in ways that are poorly understood even by modern spacecraft engineers. Atomic oxygen, single oxygen atoms rather than the paired O2 molecules we breathe, is produced by photodissociation of molecular oxygen by ultraviolet radiation. It is extraordinarily chemically reactive. It attacks polymers, metals, and organic materials aggressively. Spacecraft operating in low Earth orbit experience measurable surface erosion from atomic oxygen exposure over months and years. What it would do to mud brick and bitumen mortar over similar timescales would be comprehensive destruction. The journey up the tower, then, is a journey through a sequence of increasingly hostile environments, each one deploying a different set of physical mechanisms to attack the structure and its occupants. Pressure and oxygen depletion take the workers before 8 kilometers. Wind loading and resonance threaten structural integrity continuously from ground level upward. Temperature differentials attack mortar joints through the stratosphere. UV radiation degrades organic construction components. Micrometeorite erosion assails the upper sections. Electrical discharge conducts continuously through any conductive path reaching toward the ionosphere. Thermal cycling at the Kármán line fractures materials with every pass from shadow to sunlight. None of these are arbitrary. None of them are punishments. They are the physical character of the atmosphere, a layered system of increasing hostility to rigid surface-connected structures that has existed since the Earth acquired its atmosphere billions of years ago. The tower does not fail because it is impudent. It fails because the universe was not designed with towers in mind. Now here is the reframe, and it requires sitting still for a moment before moving on. Everything discussed so far, the compressive limits of ancient materials, the death zone, the jet stream, the thermal cycling, the electrical discharge, the atomic oxygen, has been framed as a series of obstacles, problems to be catalogued, failure modes to be enumerated. The implicit assumption running beneath all of it is that the Tower of Babel represents human ambition colliding with physical reality and losing. That the story is, at its core, a story about a ceiling, about limits, about the universe saying no. But that framing is wrong, or rather, it is incomplete in a way that changes everything. Consider what the physics is actually describing when you map it onto the Babel narrative. The atmosphere is not a wall, it is a gradient. A continuous transition from the dense, warm, pressurized, biologically hospitable environment at the surface to the cold, airless, radiation-saturated, thermally extreme environment of space. There is no single point at which the tower would fail. There is a cascade, a progressive sequence of increasing hostility that begins the moment construction rises above the surface and intensifies continuously all the way to the Kármán line and beyond. The universe does not wait until the tower is nearly finished and then dramatically intervene. It pushes back from the very first brick laid above the foundation. This is important because it reframes the Babel intervention not as a single dramatic divine act, but as something woven into the structure of physical reality from the beginning. The atmosphere was always going to do this. It was always going to thin and cool and accelerate its winds and charge its electrical gradients, and bombard anything reaching into it with radiation and micrometeorites. This was not arranged specifically to frustrate one building project on one flat plain in Mesopotamia around 3,000 years ago. It is simply what the atmosphere is, what it has always been, what it will continue to be for anyone at any level of technological development who attempts to build a rigid structure from the surface to space. And here is where the reframe becomes genuinely vertiginous. Because we have built structures that reach space, they are called rockets, and the reason rockets work where towers cannot is not that rockets are cleverer or better engineered or made of superior materials, though all of those things are true. The deeper reason is that rockets do not stay connected to the surface. They leave. They sever the physical relationship between the surface and the object in space, and once severed, the object obeys a completely different set of rules, the rules of orbital mechanics rather than structural engineering. A rocket is not at all a tower. It is a fundamentally different answer to a fundamentally different question. The Tower of Babel, as conceived, a structure physically continuous from the ground to the heavens, maintained as a fixed connection between the surface and the divine realm above, is not just difficult. It is categorically impossible. Not in the way that heavier-than-air flight was impossible before the Wright brothers, where the barrier was technological and fell when sufficient ingenuity was applied. It is impossible in the way that travelling faster than light is impossible, not a practical barrier that better engineering can eventually overcome, but a consequence of the laws that govern the universe at a fundamental level. No material assemblage on Earth's surface can form a rigid continuous structure reaching from the ground to space. The physics does not allow it. Think about what this means for the story. The conventional reading of Babel positions the intervention as contingent. God decides at a particular moment, looking at a particular tower at a particular stage of construction, to act. A different decision by the divine, and the tower continues. The story is about will. Divine will overriding human will. But if the physics is the intervention, the story changes shape entirely. There was never a version of events in which the tower succeeded. The failure was not a decision. It was a mathematical consequence of the laws of nature. The universe did not choose to stop the tower. The universe was simply itself, and being itself was sufficient. The Grand Canyon offers a useful analogy here. Imagine trying to photograph the Grand Canyon from a single fixed point, one camera, one position, capturing the entirety of a structure that is 450 kilometers long, 30 kilometers wide, and nearly 2 kilometers deep. It is not that the photograph would be a bad one, it is that no single photographic frame can contain the whole thing. The subject is too large, too dimensionally complex, too multiply-scaled for any fixed observation point to encompass. You would need to move. You would need to take thousands of images from thousands of positions and assemble them into something that approaches the whole. Our knowledge of why the Tower of Babel could not have worked is exactly like that photograph. Each physical failure mode we have examined, the material limits, the atmospheric pressure, the wind loading, the thermal cycling, is one image from one position. Each one is accurate. Each one captures something real. But no single failure mode is the reason the tower cannot be built. The reason is the totality. The fact that reality, from the ground to space, is a continuous system of integrated physical laws that collectively make the project impossible at every scale and in every dimension simultaneously. What we do not know is whether that totality was intuited in some profound and inarticulate way by the people who first told the Babel story. Whether the mythological form, the divine intervention, the confusion of languages, the scattering of peoples, was a narrative encoding of a genuine physical understanding that could not yet be expressed in the language of physics. Whether ancient human beings, looking up at the sky and feeling its inaccessibility in their bones, built a story that captured the truth of that inaccessibility more accurately than they could have known. That question cannot be answered. The evidence does not reach that far, but it is, perhaps, the most interesting question the story poses, more interesting than whether the tower could have been built, more interesting than which ziggurat inspired it, more interesting even than the physics of atmospheric failure modes. Did the ancient world know, in some way that precedes knowledge, that the sky was closed to towers? Did the intuition embedded in the myth outrun the science by 3,000 years? The universe, it turns out, had been prepared for this question long before anyone thought to ask it. There is a useful comparison to make here, and it is not the one you might expect. In 1957, the Soviet Union launched Sputnik, a metal sphere the size of a beach ball, weighing 83 kilograms, carrying nothing more sophisticated than a radio transmitter beeping at a frequency anyone with a shortwave receiver could detect. It orbited the Earth every 96 minutes at an altitude of roughly 560 kilometers, well above the Kármán line, in the silent environment that every version of the Tower of Babel was trying to reach. The people who built it did not connect it to the surface. They threw it. They used controlled explosion to sever the relationship between object and ground, accelerating it to a speed at which the curve of its fall matched the curve of the Earth beneath it. And in that elegant physical arrangement, it stayed up. Not because it was held, because it was moving. The distance between Sputnik and Babel is not merely technological, it is conceptual. The tower imagines a connection, a fixed, continuous physical link between the human world and the realm above. The rocket imagines a departure. These are not two solutions to the same problem. They are two entirely different understandings of what the problem is. And the 3,000 years separating the mythological tower from the orbiting sphere are, among other things, the time it took humanity to understand that the sky is not a ceiling to be pierced from below, but a threshold to be crossed by letting go. That shift in understanding, from connection to departure, from tower to rocket, is one of the most profound conceptual revolutions in human history. And it did not happen quickly or cleanly. It happened through Copernicus relocating the Earth from the center of the cosmos, through Newton deriving the mathematics of orbital motion and realizing in a moment of extraordinary insight that the moon is simply a cannonball, fired fast enough that it keeps missing the ground. Through Konstantin Tsiolkovsky, a partially deaf Russian schoolteacher working in near-total obscurity in the late 19th century, deriving the rocket equation that still governs spaceflight today. Through Robert Goddard launching the first liquid-fueled rocket from a cabbage field in Massachusetts in 1926, watched by almost nobody, ridiculed by the New York Times, quietly laying the practical foundation for everything that came after. Through thousands of engineers and mathematicians and test pilots and mission controllers who carried the conceptual revolution from idea to hardware to orbit across a span of decades. Each of those steps was, in its own way, a Tower of Babel problem solved by refusing the tower's premise. The question was never how to build higher. The question was how to leave. We are now, in 2024, at a moment when the descendants of Sputnik include the International Space Station, a structure roughly the size of an American football field, assembled in orbit over 13 years by 5 different space agencies, and continuously inhabited since November 2000, and a growing constellation of commercial launch vehicles capable of reaching orbit with increasing regularity and decreasing cost. We have rovers on Mars. We have a probe, Voyager 1, that has crossed the heliopause and entered interstellar space, currently more than 23 billion kilometers from the Sun, still transmitting. We have mapped the cosmic microwave background radiation, the afterglow of the Big Bang, with sufficient resolution to extract detailed information about the geometry and composition of the universe as it existed 380,000 years after its origin. And we have not built a tower. There is something worth sitting with in that fact. All of human spaceflight, all of our genuine reaching beyond the atmosphere, has been accomplished by departure rather than connection, and by severing rather than extending, by accepting that the way up is not a structure but a trajectory. The Tower of Babel turns out to be not just a mythological failure, but a conceptual dead end, a beautiful, understandable, deeply human misunderstanding of the nature of the problem. What remains unknown, and what the physics and the history together conspire to make genuinely thrilling rather than merely frustrating, is how much further the trajectory goes. The Kármán line is 100 kilometers. Low Earth orbit is roughly 400 kilometers. The Moon is 384,000 kilometers. Mars, at its closest, is 54 million kilometers. The nearest star system, Alpha Centauri, is 41 trillion kilometers, a distance so large that our fastest current spacecraft would take roughly 75,000 years to reach it. Against that scale, everything humanity has achieved in space, every orbit, and every moon landing, every interplanetary probe, represents a fraction of a fraction of a fraction of what lies beyond the atmosphere. The Tower of Babel story, read through the lens of physics, is ultimately not a story about failure. It is a story about the moment a species first looked up and understood, however imperfectly, however mythologically, that the sky was not simply the sky, that above it was something else, something vast and different and subject to different rules. That understanding, that the vertical direction is not just more of the same, but a passage into an entirely other kind of place, is the beginning of every space program that has ever existed. The ambition encoded in Babel is not wrong. It is simply expressed in the wrong medium. Stone and brick and mortar cannot take you there. But the desire encoded in those 11 sparse verses, the desire to rise, to reach, to make a name that endures, to not be scattered and diminished and forgotten, that desire is not obsolete. It is, if anything, more urgent now than it was on the plain of Shinar. Because we now know, with a precision no ancient builder could have imagined, exactly what is up there. And we know with equal precision how extraordinarily difficult it remains to reach it. The tower failed. The trajectory continues. And somewhere in the distance between those two facts lives every interesting question humanity has left to answer.